Welcome back everyone to a new school year. This time we're going to be doing Calc BC, and we're going to be doing a quick recap of Unit 1, which was limits. So first, limit notation. Before I go into limit notation, we need to know what a limit is. A limit basically shows what a value a function approaches. It doesn't tell us the exact value of a function, but instead what value it's being approached. So in order to write a limit, you'd write lim and then x with the arrow and then a number and then f of x. Now, it doesn't have to be f of x or x. It could be g of x or maybe h of a. Instead of x, we could do a. Or even instead of a function, we could put the whole equation. With limits, we can also use graphs and tables to find what number is being approached. So as the x value is getting closer to a specific number, f of x is also getting closer to a specific number. We also need to take into account the limit from the left and right side. So in this case, you can see on the left side, we have the limit as x approaches 4 with the minus symbol. That means to the left. Then we have limit as x approaches 4 with the plus symbol. That means from the right. If there's no symbol, that means it's approaching from both sides. The next picture is a quick graph of the graph just going up and down and then a short cusp basically. So if I were to take the limit as x approaches negative 3 of f of x, I can do what the curve is going to at negative 3, or just the line basically, and we can see that it gets to 1. Now it doesn't mean that it's exactly at 1, but it means it's getting close to 1. So there's a difference between taking the limit and doing f of negative 3 in this situation. So f of negative 3 would be 0 because it's a black dot, meaning that's where the actual value would be. And then finally we have a table where we have a bunch of different numbers. So we can see that on the x side, or the x row, it's getting closer to 9 because it goes from 8.7 to 8.9 and then 9.8 to 9. Now the output would be negative 5 because it goes from negative 5.8 to negative 5.001 and negative 4 and negative 4.999. So from that we can tell that the answer would be negative 5. Now we don't know that it could be negative 5, but we just know it's approaching negative 5. With limits, you can use basic algebraic properties such as addition, subtraction, multiplication, and division. These are all the ways on how it works when using limits. And then here is an example problem where you're given a table and you need to use algebraic properties to solve the limit as x approaches 5 of that big question. And then at the bottom is the example of how to do it. Now, you can also do algebraic manipulation with limits, which is basically trying to find different ways on getting a limit, because if you directly substitute or trying to plug in the number that x is approaching into the equation, you could get an asymptote, indeterminate form, which is 0 divided by 0, your answer, or doesn't exist. Additionally, with algebraic manipulation, you need to understand these 4 limits. So for sine, if the limit as x approaches 0 for sine x over x, that equals 1, no matter what. And then if you were to flip that, where it's x over sine x, that also equals 1. Now for cosine, if it's 1 minus cosine x over x, and that's when x approaches 0, it equals 0. And then if you did cosine x minus 1 over x, then that equals 0. On the right are some examples on how to do algebraic manipulation on trying to set the limits similar to sine x over x and 1 minus cosine x over x to try and get your answer. So I will quickly go over the first question. The other two you can understand that for yourselves. So we have sine 3x over x and x approaches 0. We want to make it similar to our basic limit where sine x over x equals 1. So the goal is to get the coefficients of everything to be the same. So in this case, we multiply the top and bottom by 3. And because of that, because everything has 3 in it, if we approach 0, our answer would just be 3. Next is choosing procedures with limits. As you keep on practicing with limits, you'll realize that you'll have to do different methods of trying to get a limit. In this case, you can rationalize fractions with radicals by multiplying by the conjugate, and with complex fractions, you have to multiply fractions to get the same denominator. Here is a simple example where I didn't really show all the work, but it's a shortened version of how to get these answers, because if you did direct substitution, you would get indeterminate form, which is 0 over 0. So if you want, you can pause and take a look at that. Next is the squeeze theorem. This is a very simple one. I'm not really going to go over it, but essentially, if we have three functions, f of x, h of x, and g of x, and if f of x is in between those two functions, then that means f of x will equal h of x, and h of x will equal g of x, where they're all the same values. With this, you can use algebraic manipulation if you don't have like a graph or a table, which I showed to the right, which is using algebraic manipulation. For instance, if I had the limit as x approaches 0 of x squared times cosine of 1 over x squared, we know that with cosine, it jumps between -1 and 1. So we know it could be less than or equal to -1, but it also has to be less than or equal to 1. So with that, we need to use algebraic multiplication by getting everything as x squared, and then we can take the limit of each function. So we know that if we take the limit as x approaches 0 of -x squared, it'll be 0. And if you take the limit as x approaches 0 of x squared, it'll also be 0. So because x squared cosine 1 over x squared is in between 0, that means the limit has to be 0. Discontinuities. There's 3 types of discontinuities you'll meet in limits. Jump discontinuity, removable discontinuity, known as a hole, and a vertical asymptote. Jump discontinuity is when the value of a function instantly jumps. So in this case, on the first graph, you can see how there's 2 holes and they jump. The next one is a removable discontinuity, which is a hole. The difference is that there's only one hole in this situation, where you can still take the limit, but it won't be fully continuous. As you can see, there's a blue dot at the bottom, but there's a hole. And finally, there's a vertical asymptote, where if you try and take the limit, it'll approach infinity or negative infinity. As you can see from the graph on the very right end, it's approaching infinitely towards some big number, and it never stops. And then there's some extra questions at the top right if you like to do. Now we're going to go over finding domains of functions. Before I start, you will need to know how to do interval notation with this, okay? So if you want, and if you don't know how to, I recommend practicing that. With this, you need to understand the domains of rational functions, radical functions, and natural log functions. With the rational function, the first equation on the left, you need to set the denominator equal to 0. That's where you find your vertical asymptote and you find the whole domain of the graph. Next is your radical function, the second equation, and that you would get the inner argument, or the equation inside the square root, and set it greater than or equal to 0. And finally, with the natural log, you would get the argument inside the ln and do greater than 0. Infinite limits and vertical asymptotes. You need to check if a function has an asymptote and if the limit approaches the asymptote. The only way for the limit to not exist is where it's unbounded, where in this case it's the vertical asymptote, and it approaches infinity or negative infinity. These 3 equations should be good practice on understanding infinite limits and vertical asymptotes. Limits at the infinity and using horizontal asymptotes. Approaching limits from infinity and negative infinity is very weird, basically. How it works is that a function, it can't cross a vertical asymptote, but they can cross a horizontal asymptote. You can see on this picture on the right of sine x over x as its horizontal asymptote is essentially y equals 0, where it gets pretty close to 0, and it crosses it. How it works is for a vertical asymptote, it's x equals some number, but in this case for a horizontal asymptote, it's y equals another number. The rules for a horizontal asymptote is where if you're given a fraction, you got to take the limit. If the denominator is smaller than the numerator, in this case, if the numerator is increasing by a lot more than the denominator, the answer is 0. But if the denominator and the numerator are both equally increasing by such a big number, then it equals 1. Otherwise, if your denominator is increasing by a really large amount, and your small numerator is increasing by a very little amount, then the answer is infinity. So here are 9 questions I recommend solving. These would be pretty helpful. And before I would solve them, a neat trick is when you're looking at the equations, I would focus on the number or the variable that changes by a large factor. For example, number 1, we have x squared plus 4 and 3x minus 5. The number that changes the most in the numerator is x squared. And the number that changes the most in the denominator is 3x. Intermediate value theorem. This is a short theorem on understanding how continuity works. It basically says that there's a possibility that a value could exist within some interval of a function, which relates to continuity. There are 3 rules for IVT before it can be applied. F of x needs to be continuous in an interval a to b, f of a does not equal f of b, and some value c, where f of c has to be in between f of a and f of b. If those 3 rules apply, then there exists a value c between a and b where c equals some number k.